All right, so that was a brief introduction to Bitcoin and blockchain. So initially, there was a huge hype. People thought that, there were tweets saying that, blockchain or Bitcoin is the biggest invention since the internet. So people thought that we were going to use blockchain technology for many different scenarios and many different cases. But years passed and we couldn't see many applications. Think about artificial intelligence. We always see new products, new abilities. But in the case of blockchain, we only see academic papers saying that we can use blockchain for this kind of stuff, but zero deployment. So nowadays, this is changing. We are starting to see new applications. In the case of cryptocurrencies, stable cryptocurrencies are becoming important. For instance, during now the war in Ukraine is still going, and it is hard to transfer physical money in that kind of situation. So they prefer to use, in some places, they prefer to use stable cryptocurrencies, where in the stable cryptocurrencies the amount of the value is stabilized. So that cryptocurrency is always $1 worth and that kind of stuff. So NFT is one of the other biggest uses of blockchain technology that became a huge hype. So let's talk about it briefly and explain what are the current problems, challenges, and so on. So NFT stands for non-fungible token. So there are tokens which are, you can think about tokens as creating a new cryptocurrency on top of another cryptocurrency. So in the Ethereum blockchain, there are many tokens. You can exchange them, they're identical. But in the case of non-fungible tokens, this is a non-interchangeable unit of data stored on a blockchain that can be sold and traded. So it can be any digital data, but popular marketplaces, allows you to sell images or videos that belong to you. Okay, types of NFT data units may be associated with digital files such as photos, videos, and audio. Because each token is uniquely identifiable, NFTs differ from cryptocurrencies. An NFT is merely a proof of ownership that is separate from a copyright. Okay, so NFT is not a copyright. When you buy it, it is just, you can think NFT is just like you are writing the receipt on the blockchain, not the image or the video file you are buying. They are not stored on the blockchain, but the receipt that you bought it is stored there. However, current NFT standard ERC 721 does not use hash functions to provide integrity. So this actually causes the Oracle problem. So because in the Oracle problem is that if you're selling something in the physical stuff using cryptocurrencies, you have to, somehow map that physical object to the blockchain. So this is the Oracle problem. In this case, we are dealing with digital data. And unfortunately, when you buy an NFT, only the URL of the NFT and some name and definition are stored on the blockchain. So if that URL no longer works in the future, then the NFT you bought can be lost. So here's an example that I really like. This is by Moxie Marlinspike. Probably you should have heard his name by now. The same NFT created by Moxie appears on OpenSea like this. So you can go to the OpenSea and see this NFT by Moxie. But if you look at the same NFT using the Rarible website, it appears like this. And if you buy it in your MetaMask, it will appear like this. So this causes a problem, because on a web page, when you are trying to buy an NFT, it may look like this, but once you buy it, it might look like this in your wallet. This is because the image or the hash of the image are never stored on the blockchain, so there's no way to verify or check the integrity. You are simply storing the URL. And if that URL gives you different images, in this scenario, Moxie makes a fantastic thing. So since he creates the NFT and as the URL, he sends this, he uses an image file on his own web page. Since that web page runs on an Apache server, depending on the visitor's IP address, the web page can give you, the Apache server can provide you a different image. And this is how it works. So when the OpenSea wants to see that NFT, Moxie's web server sends them this image. For Rarible, it sends this, and for the MetaMask, it sends this. So this is one of the biggest problems I see for the NFT, because if Moxie deletes that image from his web page, then none of this will appear anyway. So you have to be sure that image or video file you are buying, you should check which URL it is used for. And you don't have to use your, traditional HTTP web pages. You can use services like IPFS. But in order for that to work, people should keep sharing that image like a torrent file. And a lot of images are lost by the way. So let's talk about a little bit misconceptions that we have talked so far. One of the misconceptions was about cryptocurrencies. The name cryptocurrency suggests that they involve encryption, because people think that cryptography means encryption, but it is not. Ask ChatGPT, ask if there is any encryption involved in Bitcoin, and with very confidence, it will say that yes, every transaction is encrypted and stored in the blockchain, but it is not. And ChatGPT actually is an artificial intelligence, and it checks a lot of documents. And if a lot of people know something in a wrong way, then ChatGPT will also give you the wrong answer. Okay. So I would answer this question. Cryptography in cryptocurrencies is generally based on cryptographic hash functions, digital signatures, but of course new areas of cryptography are still involved, like zero knowledge protocols and so on. Another misconception is that people think that hashing is encryption, which is not. Okay, even go to famous companies in Turkey or in the world, you will see that they are encrypting stuff with SHA-256, which is not an encryption. Yes, we use cryptography in blockchain and cryptocurrencies. Hash functions are used to provide immutability in the blockchain. Digital signatures are used to prove ownership of digital assets in a blockchain. But with the advancements in cryptocurrencies, many other cryptographic topics found their way in blockchains, like zero-knowledge protocols, post-quantum cryptography, because current digital signature algorithms can be broken if somebody can build a huge quantum computer in the future. Lightweight cryptography, I think, is important because people are trying to use blockchains on IoT devices and so on. So having lightweight algorithms might be useful in the future. So hash functions are used for many different scenarios in blockchains, like address derivation, securing the block header, securing the block data, creating unique identifiers, creating cryptographic puzzles. So we have a lot of hash functions in the literature, but some of them are broken, like MD4, MD5, and SHA-1 are broken, and you shouldn't be using them. And there are some secure ones, like RIPE-MD, where the output is 160. So if you want a short output hash function, this is the best thing you can do. Then we also have SHA-2 and SHA-3. Bitcoin script allows the use of SHA-1, RIPE-MD 160, and SHA-256. So there are opcodes for them. But in transactions and so on, SHA-1 is never used, so we are secure in this case. So this is also surprising because initially Satoshi included RIPE-MD in the opcode. So this is also gives the idea that maybe Satoshi might be a European or have very close friends in Europe, because at the time of that, RIPE-MD wasn't a thing in the United States. Okay. So Bitcoin script uses script allows SHA-1 with the opcode op SHA-1, but it is not used in practice. Yes, RIPE-MD are used like this. And there are also different opcodes like op hash 160, which first uses SHA-256, then the output is fed to RIPE-MD 160 to reduce the the output size, and this is used in address generation and so on. Yes, Bitcoin also allows SHA-256, which is used a lot actually. If you want to use SHA-256 device, this opcode allows you to do that. In its proof of work algorithm, ETH, Ethereum uses Keccak, which is also referred to as SHA-256. But of course, it is no longer important because Ethereum no longer uses proof of work, but it's proof of stake. But since Ethereum is, I think, founded in 2014 or something, this is why they allowed to use of SHA-3, because at the beginning, when the Bitcoin was introduced, SHA-3 competition wasn't held. So this is why Bitcoin does not support SHA-3. So mining puzzles are really interesting because in the case of Bitcoin, people provided dedicated hardwares called ASICs, which can perform double SHA-256 in a very fast way. So people thought that if we use multiple hash functions, then it will be hard to produce a dedicated device for that. So this way we can keep mining with CPUs and GPUs. So there are many different mining puzzles, and one of them is X11. So there are 11 hash functions written here. Most of them are from SHA-3 competition, the finalists, and so on. So you, instead of using double SHA-256 as in the case of Bitcoin, here you are using 11 hash functions. So for instance, you take the input, fed into this hash function, the output is fed into this one, and so on. And at the end, you check if the output, after these 11 different hash functions, if the output is smaller than a value or not. So this kind of prevents the building a fast and price performance ratio good ASICs, but people did that. So some alternative cryptocurrency developers said that let's make it even more complex. Now include more functions, like 13 hash functions, again from SHA-3 competition finalists or second round candidates. And so on. As you can see, X15 uses these 15 hash functions. X16 also includes this one. In the X16 are, instead of using 16 algorithms in the specific order, every block, the order of the algorithms are randomized, which actually prevents to build a good ASIC. And finally, we have X17 with 17 algorithms. So hash functions are really used in mining and so on. Another thing we use is the digital signatures, but there's a difference here because in practice, sometimes people, when digital signatures are used, most of the time we use digital signature algorithm or the standard, which is currently going to be removed from standards because elliptic curves are more secure. So in this kind of signatures, we rely on the discrete logarithm problem. So we will actually deal with the algebra there. So currently, I haven't explained what a group is, but assume that we are working with numbers. So you have an element G, and calculating the 8 power is fast. So, but once the output is given, once you know G and B, it should be hard to obtain A. So we are trying to create a problem which is fast in one way and hard in the other way. An example can be shown as the modular arithmetic. So assume that I choose an X. So I calculate the X power of 3 modulo this number. The result is this one. And now I'm asking you, guess which X value I used. So, I mean, you can brute force the system, of course, but it will take time. And if we use bigger numbers and if we use a prime number here, the problem is a lot harder. But of course, we have to use thousands of bits, digits, not as something simple like this. In this scenario, the answer is this. But you can, if I use the 300-digit X, finding it by a brute force would be hard. Okay. So this problem is hard, but actually the hardness depends on the the group you are using. Here we are using the numbers here, but sorry. So if you use a different group, in this case, we will be talking about elliptic curves. This problem will be even harder. So aim is to define an addition operation on the elliptic curves and change this problem into adding the point on an elliptic curve x many times and giving the result, and then ask what the x is. So elliptic curves are in Bitcoin. Actually, every cryptocurrency after Bitcoin kind of uses these libraries. So most of the time, we are always using the same elliptic curve like the Bitcoin and the same implementation. So it is important to know how the elliptic curves work and how the digital signatures we use in these cryptocurrencies works. So an elliptic curve is just an equation like this: y squared equals to x cubed plus ax plus b. The result, if you want to plot it on the 2 dimensions, the picture depends on your choice of a and b. So sometimes it can be like this, but there can be, 2 pieces and so on. And we define a very different arithmetic of it. So we assume that there is a point at infinity where the y coordinate goes. So this is considered as the identity element. So when you have a point on the elliptic curve, we claim that the inverse of the point is just the reflection with respect to x-axis. We correspond it as the minus p. And if you want to add 2 points on this elliptic curve, p and q, the equations work like this. Actually, you draw the line passing these 2 points. You know that only one line can pass through 2 different points. So it intersects the elliptic curve at a 3rd point. This is due to the definition of the equation of the elliptic curve. You obtain the 3rd point, just reflected with respect to the x coordinate, and say that this is p plus q. So this is how we define an addition operation. We will see the related algebra in the following weeks, but this actually allows you to create a group operation. Here, the group operation is addition like this, and group elements are the points on this elliptic curve. So the question is, how can you add a point to itself? The picture is like this. Draw the tangent line. It has to intersect this and say that this is 2p. So as you can see, I add p to itself x many times, obtain a point here, for instance, and ask you what the x is. So discrete logarithm problem on the elliptic curves translate to this one. And since these pictures I showed you are using the real numbers, we had infinitely many points, but of course we are going to use these points in our example, so we need to use finitely many points. For this reason, instead of working over R, we are actually working over, in this picture is at 89, but we are going to use finite elements. But these equations will still hold for these points here. All right. So the following weeks will be about digital first hash functions, then digital signatures. But in order to understand that, for the digital signatures, we have to cover a little bit of simple algebra to understand rings, fields, and groups, and so on. But the question is, are these hard problems we mentioned are really hard? The answer is current technology cannot solve them, but if you can build a very huge quantum computer, all of these hard problems can be solved in polynomial time. So I mentioned about discrete logarithm problem and elliptic curve discrete logarithm problem, but we also use integer factorization problem in cryptography for RSA. And all of these algorithms can be solved in polynomial time if you have a large quantum computer. But it doesn't look like this is going to happen in the close future. So currently IBM, for instance, has 127 qubits. Some other companies have 140 qubits and so on. But to break, for instance, 80-bit security, this corresponds to RSA 1024, which is not secure nowadays. But you need to have around 2000 qubits. So you might say that, okay, if somebody has 100 qubits, maybe, in the maybe 10 years, they can have 2000 qubit quantum computer. Yes, but these qubits generally have a lot of noise. So in order to have this many logical qubits, you probably need millions of real qubits in real life. So we are not thinking that quantum computers can be built in a very short time and break all of the cryptocurrencies. But NIST is organizing a post-quantum crypto competition anyway. There are currently some finalists and so on. We have some winners, but we can add these algorithms in the future to secure our system if somebody can build such a big quantum computer. But don't forget that adding new cryptographic algorithms to a blockchain requires a soft fork. So we can solve this with a soft fork, but maybe we might also need a hard fork at the end. Okay. So there are also zero knowledge proofs. I will briefly mention what they are. Cryptocurrencies like Bitcoin provide pseudo-anonymity. To obtain anonymity, users use some non-cryptographic techniques like mixing. So instead of sending your Bitcoins to a person, you get together with many people, and in a single transaction, you transfer money to that many people again. And this way, it is hard to follow whose money went to whom and so on. Two protocols, zero coin and zero cash, provide anonymity at the protocol level by using zero knowledge protocols. Main idea behind zero knowledge protocols is that one party can prove that they know a value X without revealing it. So this is the main idea behind zero knowledge protocols or proofs. Zero coin's idea is as follows. Initially, they proposed it as a hard fork to Bitcoin, but people didn't accept it. So zero coin protocol uses two coins A and B to obtain anonymity. A user obtains anonymity by destroying A coins and instantly gaining or minting that amount of B coins. So instead of making the transactions at the blockchain of A, you do it on the blockchain of B and destroy them from there and obtain back from A. But of course, there are some limitations to this problem. A better solution came from zero cash, which uses ZK snarks, which makes zero knowledge proofs much more compact and efficient to verify. So instead of using two coins, here you can use a single coin and obtain small signatures. But of course, there are some caveats anyway. Snarks are not post-quantum secure because here you are actually using an RSA accumulator, which security depends on integer factorization problem. As I mentioned, a huge quantum computer can break it. So there are alternatives like Starks. They are quantum secure because instead of these RSA accumulators, they only use hash functions, but proof sizes are currently larger. So there are many research is going on in these areas. Finally, let's talk about why you do not need a blockchain. Because there was a huge hype and people thought that we will be using blockchain all the time. But as you can see, we are not, downloading different blockchains and installing it on our laptops because there isn't much deployment. There are a lot of ideas, but people misunderstood a lot of stuff. So most of the ideas are wrong. Most of the academic papers, master or PhD theses in this area are wrong or redundant. So first you have to decide why you need a blockchain. So a blockchain might be useful if a shared and consistent data store is needed. Data is contributed more than one entity or auditing is required. Records are never updated or deleted after they are written. Sensitive data will not be stored as plain text. Control of the data store cannot be assigned to a single entity, and tamper-proof log of all data store rights is wanted. So if you want to use a blockchain for a problem or for a scenario, you have to answer yes to all of these questions. If one of them you can say no, then this means that most probably you don't need a blockchain. Maybe you can solve that problem more efficiently using other known techniques. Okay, so this is why we don't have much, deployment of blockchains. So new ideas are coming. Currently, we are seeing them, but since Bitcoin, now it is 14 years, and we haven't seen much. This is because people misunderstood most of the ideas behind blockchain, and people didn't understand the crypto part of this blockchain. So in academic papers, as I said, we see some strange claims or wrong results. So if you want to use a blockchain, you have to answer yes to all of these questions, and then maybe you can use a blockchain, or a blockchain might be useful for you. So this should be always kept in mind. Otherwise, because people know that the blockchain is immutable, so just focusing on this idea, they say that, okay, we can use blockchains to do this and so on. Again, even if you use it for that problem, if you calculate the size of the blockchain, you can easily see that it exceeds a few terabytes in a few weeks. So you have to consider all of the use cases, and you have to actually maybe deploy it and use a toy case and see if it really works.